Out there in the silent, unending dark, a ghost is moving. It is an object born from the primordial cold, a traveller from a realm so distant it defies human comprehension. For millions of years it has fallen a solitary pilgrim on an immense, lonely trajectory toward a fire it has never known. This celestial wanderer was not supposed to survive its destination. It was meant to be an offering consumed by the star it came to visit. But something remarkable happened. It endured the inferno, and when it emerged from the glare of our sun, it was transformed. No longer a pristine spectacle of ice and dust, it now burns across our night sky with an unsettling otherworldly fire. A strange, smouldering colour like ancient embers or cooling gold. This is the story of a survivor. A cosmic riddle painted in hues of amber and deep red. It is the mystery of C2025 K1 Atlas, the sundiver that returned from its ordeal, bearing a scar of light that challenges our understanding of these ancient visitors from the dawn of time. Why does its colour shimmer with such a peculiar alien glow? The discovery was almost impossibly subtle, a faint whisper of light captured by the unblinking eyes of a machine. On a remote mountaintop shielded from the glow of civilization, the Asteroid Terrestrial Impact Last Alert System, or ATLAS, conducts its nightly vigil, a silent guardian against cosmic threats. Its robotic telescopes methodically scan the heavens, creating a colossal cinematic record of the moving universe night after night. Within this torrent of data, sophisticated algorithms search for anomalies for points of light that refuse to stay put, that betray their motion against the steadfast backdrop of distant stars. It was here, in a routine digital survey, that a new traveller was found. At first it was just a few smeared pixels, an indistinct smudge so faint it was barely distinguishable from background noise. Yet it was moving. It possessed a purpose. Following protocol, the celestial object received its designation, a name that is less a title and more a cosmic address. C for a non-periodic comet, an emissary on a path so vast it will not return within a human lifetime, or perhaps ever. 2025 K1 marks the year and the sequence of its discovery, and Atlas, the name of the vigilant robotic sentinel that first saw it, a cold technical label for what would become a spectacle of profound beauty. Initial calculations of its orbit revealed a story of epic proportions. This was no short-period traveller from the nearby Kuiper belt. Its trajectory was a vast parabolic arc, a line stretching back into the deepest, most remote region of our solar system. This icy pilgrim had begun its journey in the Oort cloud. To speak of the Oort cloud is to speak of an empire of ghosts. Imagine our solar system not as the familiar disk of planets we see in textbooks, but as a tiny, vibrant city centre. Now envision a vast surrounding countryside, sparsely populated and stretching for immense distances in every direction. This countryside is the Kuiper belt home to Pluto and other icy worlds. But the Oort cloud exists on a scale that dwarfs even this. To truly grasp its immensity, let us construct a mental model. Picture the sun as a single gleaming grain of sand held in your palm. At this scale, the Earth would be a microscopic speck of dust orbiting about 3 inches away. Jupiter, the king of planets, would be a slightly larger dust mote, a little over a foot from the central grain of sand. The edge of the Kuiper belt would be found about 10 feet away. On this scale, where would the Oort cloud begin? It would not start in the same room. It would not even begin in the same building or on the same street. The inner edge of this tremendous spherical shell of frozen relics would start more than a mile away from that single grain of sand, and it would extend outwards for tens, perhaps hundreds of miles. A stupendous ethereal sphere encasing our entire solar system. This is the ancestral home of C 2025K1 Atlas. It is a realm of absolute cold and profound darkness, where trillions of icy bodies, remnants from the planetary construction yard, drift in a slow cosmic ballet barely tethered by the sun's faint gravity. They are the pristine, unaltered building blocks of our worlds, frozen in time for 4.5 billion years. Each one is a time capsule from the very beginning. For eons, our comets slumbered in this frozen wilderness. But the galaxy is not a quiet place. The subtle gravitational caress of a passing star or the imperceptible tidal pull of the Milky Way itself can disturb these delicate orbits. A tiny nudge, a cosmic push, no greater than a whisper, is all it takes to send one of these dormant bodies on a new path. A path of no return, a long, slow, inexorable fall inward. So began a journey that is almost impossible to imagine. For 1,000,000 years, or perhaps longer, C2025 K1 fell. It tumbled through the void, a dark, inert rock of ice and dust, its surface temperature hovering just a few degrees above absolute zero. It passed through the domains of Neptune and Uranus, silent and unseen. It crossed the orbits of Saturn and Jupiter, still a frozen ghost, offering no hint of the spectacle it would later become. As it journeyed deeper into the sun's territory, warmth began to touch it for the first time since the solar system's birth. The distant sun, once a star no brighter than any other, grew in power. Its radiation, a gentle pressure at first, began to stir the ancient ice. On the comet's surface, molecules that had been locked in a frozen matrix for billions of years began to feel a new energy. The process of sublimation started a magical transformation. Ice turned directly into gas, erupting from the nucleus in great jets. This escaping vapor carried with it countless particles of dust, creating a vast, glowing shroud around the solid core. This luminous atmosphere, the coma, swelled to a size that could dwarf planets, a temporary world of gas and light. The pressure of sunlight and the solar wind then began to push this material away, sculpting it into two magnificent streaming tails. One tail, composed of ionized gas, pointed directly away from the sun, glowing with an ethereal blue light as it fluoresced. The other, a broader, more curved fan of dust, reflected the yellow-white sunlight trailing behind the comet in its orbital path. This was the classic, beautiful form of a great comet, a celestial spectacle that has inspired awe and terror throughout human history. But for C2025 K1 Atlas, this was merely the prelude to its true test. Its orbit was not just a flyby of the inner solar system. It was a direct, terrifying plunge toward the sun itself. It was a designated sungrazer, a member of a rare and often doomed class of celestial objects that pass through the sun's extended corona. This is a journey into a literal hell. As it neared perihelion, its closest approach to our star, the environment became unimaginably hostile. The temperature on its sun-facing side soared to thousands of degrees, hot enough to vaporize rock and melt iron. The sun's radiation, now a relentless photonic blizzard, blasted its surface, eroding it, boiling away tons of material every second. But the greatest danger was the gravity. The sun's immense gravitational field exerted colossal tidal forces on the comet's fragile, loosely packed nucleus. Imagine holding a ball of loosely packed snow and swinging it around your head on a string faster and faster. The centrifugal force wants to tear the snowball apart. For the comet, the sun's gravity was pulling on its near side with immensely more force than on its far side. This differential force stretched and squeezed the icy core, trying to shatter it, to pulverize it into a cloud of dust and gas. We have witnessed this execution before. In 2013, the world watched as Comet Ison, hailed as a potential comet of the century, made a similar perilous dive. It approached the sun as a brilliant, vibrant object, but it never emerged. The combined fury of heat and gravity was too much. Ison disintegrated, its substance scattered into a faint glowing smear, a momentary sacrifice to the star it so closely grazed. This was the expected fate of C2025 K1 Atlas. Astronomers watched their instruments trained on the sun's corona, expecting to see a final brilliant flash, and then nothing. The comet disappeared behind the sun into the blinding glare. The vigil began. Hours turned into a day, then two. The calculations predicted when and where it should reappear, if it survived. And then, against the odds, a signal. Faint at first, a ghost against the backdrop of the corona. Something had come through the fire. As it pulled away from the sun, moving back into the view of Earth's telescopes, it became clear that this was not the same object that went in. It was a survivor, but it was profoundly altered. The brilliant whitish-blue spectacle was gone. In its place was something strange, something alien. The comet now glowed with a deep, smouldering color. a burnished golden red hue that seemed to emanate from its very soul. It was not the color of pristine ice reflecting sunlight. It was not the azure shimmer of ionized gas. This was the color of rust, of embers of dried blood on ancient stone. The survivor had returned from its trial by fire wearing a new mysterious cloak. The central question echoed through observatories worldwide: what happened? To decipher this cosmic message written in light, scientists turned to one of their most powerful tools, spectroscopy. The principle is as elegant as it is profound. When light from a celestial object is passed through a prism or a diffraction grating, it is split into its constituent colors, a rainbow, otherwise known as a spectrum. But this is no ordinary rainbow. Imprinted upon it are dark or bright lines, a unique barcode that reveals the chemical elements and compounds present in the light source and the physical conditions they are under. Every element, from hydrogen to sodium to iron, absorbs and emits light at its own specific, unchangeable set of frequencies. This cosmic fingerprinting allows astronomers to analyze the composition of stars and galaxies billions of light years away. Now, this technique was focused on the comet's strange ruddy glow. The spectrum of C2025 K1 Atlas was unlike any typical comet. The familiar signatures were there: water, carbon monoxide, but they were overwhelmed by a broad, continuous emission in the red and orange parts of the spectrum, with a steep drop-off in the blue and green. Something on or around the comet was either selectively emitting red light, or more likely, was exceptionally good at absorbing blue light, leaving only the warmer colors to reach our telescopes. The investigation had begun, and three primary hypotheses emerged. The first possibility delved into the very heart of the comet, its nucleus. Perhaps this was no ordinary cosmic snowball. What if C2025 K1 Atlas was born with an unusual composition, a recipe of primordial materials fundamentally different from other comets? Astronomers know that the outer solar system is home to a class of complex organic molecules known as tholins. These are not life, but they are reddish, tar-like substances created when ultraviolet light from the sun irradiates simple compounds like methane and ethane over immense timescales. We see these reddish materials staining the surfaces of distant worlds like Pluto and many Kuiper Belt objects. Perhaps this particular comet was formed in a region of the primordial solar nebula that was exceptionally rich in these organic precursors. If its nucleus contained a high percentage of these complex reddish tholins, the intense heating during its solar pass would have vaporized them along with the ices, releasing a vast cloud of reddish organic dust. The comet's strange color would therefore be an intrinsic property, a revelation of its unique and ancient chemical heritage. It would be a messenger from a forgotten corner of the solar nursery telling us that the ingredients for life, or at least its complex precursors, were not uniformly distributed 4.5 billion years ago. This particular wanderer would be a clue to the chaotic and diverse chemistry that reigned before the planets were fully formed. A compelling idea, but it was just the beginning of the inquiry. The second hypothesis was not about what the comet was made of, but what the sun did to it. This theory posits a dramatic, transformative event during perihelion. It suggests that the surface of the comet was literally cooked, forged into something new in the crucible of the solar corona. To understand this, we must think of the comet's nucleus not as a solid block of ice, but as a porous, fragile aggregate of ice and dust, often described as a dirty snowball. Let us imagine a piece of porous, unfired clay straight from the Earth. It is soft, fragile, and a dull greyish-brown colour. It is a mixture of fine mineral dust and water. Now place this piece of clay into a kiln, an oven of immense heat. As the temperature rises, the water within it boils away, escaping as steam. The mineral particles are forced closer together. At a critical temperature, a process called sintering occurs. The surfaces of the tiny grains begin to melt and fuse together, locking into a hard, durable ceramic structure. The clay is transformed into brick or pottery. Its color changes, often becoming a rich reddish-brown as iron compounds within it oxidize. The cosmic kiln hypothesis suggests a similar process occurred on the surface of C2025 K1 Atlas, but on an incredible scale and at an astonishing speed. As the comet plunged through the sun's corona, the intense heat was not uniform. It was a blast furnace, focused on its sunward face, this wave of extreme heat would have flash-baked the surface. The more volatile ices like frozen nitrogen and carbon monoxide would have vaporized almost instantly in explosive jets. Water ice would have followed, creating a powerful outgassing process. But what about the dust, the silicates, the carbonaceous material, the complex organic molecules embedded within the ice? They would have been left behind on the surface, subjected to temperatures of thousands of degrees. In this cosmic kiln, the fine dust particles could have sintered, fusing together to form a brittle, porous crust. Organic molecules would have been carbonized, broken down, and reformed into new, more complex and darker, redder compounds. Any sodium or other metallic elements present would have been vaporized and recondensed on dust grains, potentially altering their color. According to this model, the comet that emerged from behind the sun was wearing a newly forged mantle. It was encased in a thin, fragile crust of heat-altered material, a reddish sintered shell created in the moments of its closest approach. The golden red glow we see is therefore not from the comet's original composition, but from the light scattering off this new baked surface and the altered dust particles being shed from it. The comet is a survivor, but it bears a visible scar of its ordeal. It is a cosmic brick, fired in the greatest kiln in our solar system. This idea is incredibly appealing because it links the strange color directly to the most dramatic event in the comet's recent history. It suggests a dynamic, transformative process rather than a static, innate property. It paints a picture of a worldlet being fundamentally remade in a trial by fire, its very skin changed by its near-death experience. The color becomes a badge of survival, a testament to the inferno it endured. But there is a third, equally fascinating possibility, one that has less to do with chemistry and more to do with physics and perception. This third avenue of investigation focuses not on the source of the light, but on how that light travels through the comet's dust and reaches our eyes. It is a hypothesis rooted in the same phenomenon that paints our own skies with the brilliant colors of sunrise and sunset. The light from our sun is white, a mixture of all colors in the spectrum. However, the Earth's atmosphere is filled with tiny molecules of nitrogen and oxygen particles, far smaller than the wavelengths of visible light. These tiny molecules are exceptionally good at scattering short-wavelength light, like blue and violet. As sunlight streams through the atmosphere, the blue light is scattered in all directions, bouncing from molecule to molecule. This is why the daytime sky appears blue. We are seeing this scattered blue light coming at us from all over the atmosphere. The longer wavelengths, the yellows, oranges, and reds, are far less affected and tend to travel in a straighter line. Now consider what happens at sunset. The sunlight we see is no longer coming from directly overhead. It has to travel through a much thicker slice of the Earth's atmosphere to reach our eyes along the horizon. This longer journey means the light encounters many more scattering molecules. By the time it reaches us, almost all of the blue light and much of the green has been scattered away from our line of sight. What remains, what successfully completes the journey, is the resilient, long wavelength light. The brilliant oranges, the fiery reds, the soft golds. The sunset is not a new color being created. It is what's left over after the blue has been filtered out by the atmosphere. The third hypothesis for C2025 K1 Atlas applies this same principle to the vast cloud of dust surrounding the comet. What if the encounter with the sun did something very specific to the dust particles being ejected from the nucleus? The intense heat and violent outgassing could have fractured the silicate and carbonaceous dust into particles of a very particular size and shape. Perhaps the solar furnace preferentially created a huge abundance of dust grains that were perfectly sized to scatter blue and green light very efficiently, while allowing red and yellow light to pass through. When we look at the comet, we are not seeing the nucleus itself, which is a tiny point just a few miles across. We are seeing the sunlight that has traveled through the coma, this immense atmosphere of gas and dust that surrounds the nucleus. If this dusty shroud is filled with these specific blue scattering particles, it would act like a colossal version of Earth's sunset atmosphere. The light from the sun would pass through it, have its blue components scattered away in all directions, and only the remaining golden red light would continue on its journey towards our telescopes. In this scenario, the comet's nucleus might not be red at all. The glow we observe would be an optical illusion, a trick of the light created by the unique properties of the dust it sheds. The color would be a temporary condition, a direct consequence of the freshly pulverized dust created by the solar encounter. As the comet moves away from the sun and the violent outgassing subsides, the nature of the dust it ejects might change, and its color could slowly fade back to a more conventional hue over months or years. The weird glow would be the fleeting blush of a world shedding its skin, so we are left with three compelling narratives. Is this a comet born different, a rare specimen from a chemically unique region of the solar nebula? Its color, a badge of its ancestry? Is it a transformed survivor, its surface flash-baked into a new ceramic-like crust, its glow the scar tissue of its fiery passage? Or is it a master of illusion, its color, a temporary effect of light, filtering through a specially sized cloud of dust, a cosmic sunset wrapped around a core of ice? The truth may be a combination of all three. Perhaps the comet's unique initial composition made its surface more susceptible to being cooked by the sun, which in turn produced a type of dust that is exceptionally good at scattering blue light. Nature is rarely simple, and its most beautiful mysteries often have layers of interconnected causes. Untangling them is the great detective work of science. Whatever the ultimate explanation, C2025 K1 Atlas serves as a profound and beautiful reminder. These comets are not just transient celestial fireworks. They are messengers from an almost unimaginably distant past. They are the most pristine samples we have of the primordial cloud of gas and dust from which the sun, the earth, and we ourselves were born. They carry within their frozen hearts the chemical story of our origins. This particular survivor, this golden red emissary, brings a unique chapter of that story to our doorstep. Its altered state provides a natural experiment of incredible value. It shows us what happens when these primordial materials are subjected to extreme heat and radiation, mimicking conditions that might have occurred in the inner regions of the solar nebula during planet formation. By studying its strange light, we learn more about the resilience and the transformative potential of the very stuff we are made of. Now its journey takes it away from us. Having survived its appointment with the sun, it is now heading back out into the fathomless dark from which it came. Its path is a vast, open-ended hyperbola, a trajectory of escape. It will cross the orbits of the outer planets, once more silent and cold again. Its spectacular, ruddy glow will fade as it recedes, until it is once more just an inert, frozen rock, invisible to our most powerful instruments. It will likely never return. It is a fleeting visit, a momentary intersection of our world with a history that is billions of years old. We are a species that has evolved to look up to wonder and to question. We build observatories on mountaintops to catch the faint whispers of light from objects like this, and from them we piece together the grand narrative of the cosmos and our place within it. See 2025 K1 Atlas, the golden red survivor, is one such whisper. A fleeting, beautiful puzzle that reminds us that the universe is not only more vast than we imagine, it is more surprising, more complex, and filled with more fiery, transformative beauty than we can ever know. And the silent dark between the stars is filled with more such stories waiting for their time to fall toward the light, undefined.